topic in combinational logic design is multiplexer. Multiplexer is having many inputs and one output. So there is a select line in between these which will connect according to input to the output. So for that we are using a select line. So let us start with the first example. So that is the 2:1 multiplexer. So for 2:1 multiplexer there are two inputs. So let us say it is D0 and D1 and one output line and one select line. Now depending on select line, appropriate input line will be connected to output. So if S is equal to 0, so here is a switch or data connector you can say. So D0 line will be connected to Y, and if S is equal to 1, so that time D1 line will be connected to Y. So that means if I have to write down this multiplexer with respect to equation, it will be written like this: Y is equal to D0 into S bar plus D1 into S. And suppose I want to represent this multiplexer using gate, so I can use this equation. So the input for this one is D0 and S bar and D1 and S. So both can be OR together to get the final output. So this is the logical representation of the multiplexer. Now this is the 2:1 multiplexer. Similarly 4:1 multiplexer is designed. In 4:1 multiplexer, inputs are having 4 lines and output is 1. So input is, let us say, D0, D1, D2 and D3. And to select these 4 inputs, we are having 2 select lines, S0 and S1. So again, based on the select lines, appropriate data line will be, input line will be connected to the output. So if S0 and S1 both are 0, 0, so that time D0 line will be selected. If it is 0, 1, D1 line will be selected and then connected to the output. If it is 1, 0, then D2 line, and if it is 1, 1, the last is D3 line will be connected to the output. So similar to 2:1 mux, equation for the 4:1 mux also is written and designed using logic gates. So for this, the equation will be written like this: S0 bar, S1 bar, S0 bar, D0 plus S1 bar, S0, D1 plus S1, S0 bar, D2 plus S1, S0, D3. So this is nothing but the output of the multiplexer. Okay, so this thing can be again used or implemented using logic design with the 3 input AND gate. So input will be S1, S0, S1 bar, S0 bar and D0. Similarly, one more NAND gate, and this is how the 4 NAND gates can be used, which output will be given to the 4 input OR gate, and the final output is nothing but the output of the 4:1 mux. The next is 8:1 mux. So it is very much similar with the 4:1 mux or 2:1 mux. In 8:1 mux, the select lines will be 3, S0, S1, S3. Input lines are 8 and one output line. So if your select lines are 0, 0, 0, the first data line will be selected, and if it is 1, 1, 1, last data line will be selected. So based on the select line status, any input line will be connected to the output. Same thing happened with the 16:1 mux. So now let us go for the next topic. So that is called as a multiplexer tree. This is very important exam point of view. Multiplexer tree is a concept when higher version of multiplexer has to be designed using lower version. So that time the design is called as a multiplexer tree. So for example, let us say the using 4:1 mux, 8:1 mux has to be designed. So let us see the procedure of designing 8:1 mux using 2 4:1 mux. So in this case, we are using a enable pin. So these are the 2 4:1 muxes, which is having total 4 input lines each and 1 output line. So let us say this is Y1 and this is Y2. So for designing a multiplexer tree, we are going to use a enable pin because if we write a truth table for the 8:1 mux, so truth table will come like this: S0, S1 and S2 and my Y. So if S0, S1, S2 are 0, 0, 0, that time D0 line should be selected. When it is D0, 0, 1, D1 line should be selected. So on with all ones. So that time D7 line should be selected. This is the truth table for the 8:1 mux. So if we see in 8:1 mux, we require total 3 select lines. Whereas in 4:1 mux, we are having only 2 select lines which can be shorted together for the interfacing. We require one more select line, so that is nothing but the S2. What we can do, there are enable pin for each multiplexer. So that enable pin we can use for the third select line. Okay. So if I use the structure like this, okay. So here what will happen now? This enable line will act as a third select line. Okay, now see, we can relate this thing with the truth table. So when my S0, S1 both are 0, 0 and my S2 is 0, so what will happen here? This S2 will be inverted by this inverter and enable pin is high here. So as this enable pin is high, what will happen? This upper 4:1 multiplexer will be enabled and D0 line will be selected as S0, S1 are 0, 0. Now this line will be connected to Y. Although S0, S1 of this is enabled, but here the enable pin of lower multiplexer is disabled, as over here S2 is 0. Similarly, if I go for the 0, 0, 1, what will happen? This is the 0 again, which is inverted, and upper multiplexer is enabled and lower is disabled. Here as it is 0, 0, 1, the D1 line will be connected to Y1. So this thing will continue up to 3. After 4, what will happen? S2 is 1 now. So when S2 will become 1 here, what will happen? This inverter will make this 1 0. As this is 0, this one will be disabled and this one will be connected to the lower multiplexer, and now lower multiplexer is activated. So see, here for first 4 combinations, upper multiplexer is selected and D0 to D3 line is connected to Y1, and lower 4 combination, the next, that is a lower multiplexer is selected and those select lines or those input lines are connected to the Y2. The final output we can get by XORing the output of both the multiplexer. So this is called as a multiplexer tree, that is using lower multiplexer we can go for the higher version. So similar to this, we can design 16:1 multiplexer using 8:1 multiplexer, or 16:1 multiplexer using 4:1 multiplexer. So all these combinations are called as a multiplexer tree.